It's a pleasure to introduce Guiseppe Cannizzaro from Warwick University, who's going to give us a seminar about driving diffusive systems in the critical dimension.
Okay, thanks a lot. Well, thanks a lot for the invitation, Milton, and for you all for being here. It's my first time in Rio, and I hope not the last. Let's see how I do today. So what I want to talk about today is, it concerns mainly a couple of joint projects. One is with Quentin Moulard and Fabio Toninelli, both of whom are at TU Vienna. And the other is also with Tom Klose, who's a former postdoc of mine, now he's in Oxford. So the goal of this talk is to present, well, results and an approach thanks to which we can obtain the large-scale behavior of stochastic partial differential equations, or more generally, certain statistical mechanic systems which are stationary and at the critical dimension. Now, the class of systems we can work on are various, and I'll try to present a few, or at least I'd like to mention a few at the end of the talk, but throughout I'm going to focus on a specific example. Well, first because I think it's an interesting example in its own right. It's the first on which we implemented our strategy, and I think it has nice connections with a lot of the works people are doing or have done here at IMPA. So the object the model that we will consider are driven diffusive systems, and in particular is a stochastic partial differential equation which takes this form: dt eta equal to a half Laplacian eta plus, and now let me write it in purple if you can see it, f of eta plus xi. Now this is a stochastic partial differential equation of evolution type, and the evolution of my system, which is eta is a scalar, is driven by a space-time Gaussian white noise. So it's random, and this driver is a vector, and it's simply given whose entries are independent space-time Gaussian white noises. I mean, possibly most of you are familiar with it. If not, simply think of it as an extremely rough object. So it's a Gaussian field in which you have independent Gaussian random variables indexed by space-time by space-time points, and at each point the variance is plus infinity. So it's extremely rough. Okay. So this is our noise. Eta is a scalar, as I said, and then we have a nonlinear term. In this nonlinearity, W is a given vector on Rd. And just for convenience, you can think of it as having norm 1, but it makes no difference. So in particular, this object is nothing but the gradient in the direction w. Okay? And now what is f? F is a function. It's simply a function, let's say, from R to R. The
white space-time?
White space-time, yes.
What's the
The covariance essentially is like this. So so if I take my psi, this is psi1, psi d, and if I look at the covariance at two space-time points, and let's say I and j, as well, this is a delta function. So it's delta ij, but it's also delta at 0 of s minus t and delta 0 at x minus y. So it's totally uncorrelated at different space-time points, and also the entries are uncorrelated. Okay. Okay. So the most famous, the most famous, at least to me, the most famous of these equations is the one in which the function f is taken to be quadratic, and f of eta is given by lambda times eta squared. Now, I want to put this lambda explicitly, and with this choice of f, this is the so-called stochastic Burgers equation, because lambda, it's a constant, it's a strictly positive constant, and can also be called the coupling constant because it somehow allows you to tune the strength of the nonlinearity. But okay, you can even forget about lambda, and we want to see, okay, but it's going to play some role in what follows. Now, an interesting feature of this equation is clearly that if I choose f equal to 0, or in that choice lambda equal to 0, then the equation becomes linear. In particular, the solution, even though rough, is explicit, and it's Gaussian. So we know everything about this. Okay? So the goal is going to be to understand what is the effect of this nonlinear term. Now, before delving into the details, let me try to motivate why we want to study something like this and where does it come from. Now, this is as an equation, something similar to this was introduced by Van Beijren, Kutner and Spohn in 86 as a mesoscopic model for driven diffusive systems with one conserved quantity. Now, what does it mean? So we have mesoscopic for driven diffusive systems with one conserved quantity. Well, okay, in order to break this definition down and try to understand what these various terms are and how they arise and what's the corresponding term in the equation to each of these terms, let's try to start from a simpler system that you all know, which is the asymmetric simple exclusion. So we are in a grid. We have particles hopping around, okay? And each of these particles perform independent random walks, but when a particle attempts to jump to an already occupied site, the jump is suppressed. And what I want to assume is that the random walkers are asymmetric, meaning somehow that the probability, so that they have a preferential direction, so they prefer to jump in a given direction. Let's say that this direction is the first coordinate vector, and so they are gonna jump at rate 1 up and down, but they're gonna have an asymmetry. So it's gonna be, so they are gonna prefer to jump on the right, okay? And this is gonna be my vector W, by the way. So now, okay, so in this case, so one of the important features of the asymmetric simple exclusion process is that it has a conserved quantity. And the conserved quantity is the total number of particles, it's the total mass, because there is no mechanism that inserts new particle or removes particle. Good, so we have the one conserved quantity, excellent. And now our goal is to study this conserved quantity. But now, what are the mechanisms that drive these dynamics? So let's say we have the conserved quantity is, let's say, the density. And then we have two mechanisms, the diffusion, because each of the particles is performing independent random walks. So we have a diffusion mechanism, so that is the simple random walk, and that's represented in my equation by the Laplacian. And then we have a second effect, which is a drift. So because each of these particles actually is not simply a simple random walk, it's a random walk with a drift, and the drift points in a given direction. So this drift is somewhat parametrized by two numbers. One is lambda, the complete constant, and one is a vector, my vector W, that tells us the direction of this drift. This is lambda and W. And so, how do they act? Well, the diffusion tends to spread the particle isotropically in every direction, so to spread my mass isotropically in every direction, while the drift tends to push all of the particles in a given one. The two are competing, and we want to understand the effect of this. There is an extra feature that this model has, and is the fact that, like, if I look at product Bernoulli, this is invariant. Okay, so just keep it in mind. Now, what is our goal? So what is it that you want to do when you start with this microscopic system? Well, the first thing you want to understand is, okay, so I look at the conserved quantity, I look at the density. And the first question is, what is the macroscopic behavior? So you need to imagine something like this. I want to, so at the beginning I was on ZD. Now I want to rescale my grid, so to make the distance between different points smaller and smaller. Let's say of order 1 over t. So this distance is tau to the minus 1. Tau is going to be always large for me. And okay, so what is it that I see? Well, I'm going to see something very rough. Okay, so this is sort of my microscopic density if I simply zoom out. And the first question is, okay, what do I see at large scale? So what is the macroscopic profile? What is the average profile that this density field satisfies? So this is nothing but the so-called hydrodynamic equation, which is going to be something like this. Okay, so this is the microscopic. So in white we have microscopic. In green I'm writing macroscopic. And so what is the scale at which I see the macroscopic profile? Well, for this type of driven diffusive system in which you have an asymmetry, the dominating term in my dynamics is precisely going to be given by the drift. So we need to go to this hyperbolic scale, and the type of equation that we obtain is the so-called hydrodynamic equation. Which is a hyperbolic equation which takes this form. dtu, where u is going to be my macroscopic profile, is going to be equal to what? As I said, what I see is simply the effect of the drift. So what I see is precisely something of the form, so the direction in which the drift takes place, and then some function of u. Whatever this function is. And this function is clearly very much model dependent. In the case of the asymmetric simple exclusion process, we know what it is. This is nothing but u times 1 minus u in dimension 1. In higher dimension, it would depend on the direction that you're picking, okay? Good. So this is the first information that we get. This is the macroscopic profile, but this is not universal. It's going to depend very much. It's going to depend very much on the features of my system. So we want to move a step forward, and we want to understand what are the mesoscopic fluctuations around our macroscopic profile. So in other words, I want to zoom in on a spot in which sort of my macroscopic profile is flat, because we can simply assume that this is somewhat smooth. And I want to zoom in again. So what is it that I see? I see essentially, so I have a sort of flat macroscopic profile. I had the wild oscillations of my microscopic system, and then I want to look at what are the universal fluctuations around it. Okay? Good. And so, but these fluctuations, so we are at a mesoscopic scale. So before microscopic, we went to macroscopic, and now we want to go somewhere in between. In other words, we want to describe if, like, my rho was my density, rho tau is my scale density, so living on this small grid, I would like to write it as some sort of macroscopic profile u plus the fluctuations, but the fluctuations are going to be lower order. So something like 1 over square root of tau, so they are smaller compared to u, of eta. And now what is the equation that eta satisfies? So we're talking about fluctuations, and we want now at this point, since we are zooming in again, we start seeing again the effect of the diffusion. So in particular, we can expect to have some sort of Laplacian. This is the effect of the random walk, which now I start seeing again. Plus I need to have a noise, because we're talking about fluctuations. And how do we pick the noise? Well, okay, so for the noise we want a few features. We are in a sort of central limit theorem type regime, so we want it to be Gaussian. Moreover, we expect these fluctuations to be Markovian, because we started from a Markovian system, and so we take it right in time. And then, well, we're describing the fluctuations of the conserved quantity. So we don't want the noise to add new mass to the system, and that's the reason why we take it in divergence form. Okay, so because in this way, this is sort of an object which has mean 0. Okay, but then the drift survives. But the drift now lives at a smaller scale. So this is 1 over square root of tau. So I want to take, essentially, I'm looking at an area in which my macroscopic profile is flat. So I can take it simply to be 0. And now I want to expand this function f around 0, so around my macroscopically flat profile. So what do I see here? Well, here I'm going to see, again, W scalar gradient, and then multiplied by what? And this it's still there, but it's going to come later. So here we're going to have, okay, f at 0, plus f prime at 0 times eta, plus, and then I'm simply doing a Taylor expansion, eta squared, plus And I'll stop, I promise. 6 eta cube plus more terms, and then I have still my noise. Okay, good. But now let's look at this equation. Well, in this equation here I have a gradient. So in particular, this term I can neglect. The second term, well, this second term is linear in my eta. So I can always remove it by going to a moving frame. So it's a so-called Galilean transformation, or more simply, it's a change of variable. So this can also be removed. So the first term which I cannot remove is the square, eta squared. So then what the physicists say is, OK, all the other terms are going to be smaller. So the only term I keep is this term, and all of a sudden I obtain exactly my f of eta. And this heuristic somehow suggests the way in which I should choose this lambda. So this lambda should be the second order the coefficient of the second order term in the Taylor expansion of my function f divided by 2, whatever. So there is somehow it gives you a correspondence. OK, good. So what is it that we want to do now? Well, we would like to understand first, what is the meaning of that equation, even when we have simply eta squared? So is it true that the nonlinearity is relevant? So does it affect the linear dynamics? Or we want then to understand what are the scaling exponents, and ultimately, if we manage to express what is the scaling limit. In 1D is KPZ, exactly.
And in one dimension, it's kind of scalar version, but different from.
It's not KPZ, and you're spoiling the rest of the talk, but like, the other dimension is Gaussian, actually. But the scaling exponents vary, yes. So now, what I want to do first, before delving into the details, is okay. How do we guess, at least, whether something is relevant or not relevant, and what is the type of behavior, and how did the physicists neglect all the other terms? So the type of heuristic you want to do is okay. So what is the size of the fluctuations generally? So how do we need to scale the system to see the fluctuations? Well, the natural scaling, in which we start seeing something diffusive, is the scaling of the stochastic heat equation. So this is the typical size of the fluctuation, is the equivalent of the central limit theorem, but for space-time fields. So the way in which you do it is you take, OK, let's formally say my eta solves this equation. What is the equation which is solved by eta tau? Now tau is large at point t and x, which is equal to t to the d divided by 4 eta tau t, tau to the 1/2 x. This is the usual diffusive scaling. Okay. Now, how is the equation above affected by this scaling? Well, okay, the linear part is not affected because we know that the equation is invariant. This is sort of the property of the stochastic heat equation. What happens here? And okay, let's say that it's actually better if I rewrite it. So as we said, we see eta tau equal to Laplacian eta tau plus. Okay, let me already neglect the linear contribution and the constant. And now before I do it wrong, so the term that I see is 1 minus d12 eta, and there is clearly the gradient eta squared. The next is going to be 1 minus tau to the minus t divided by 6, eta cube plus so and so forth. And in general, the mth term is going to be of the form tau to the 1 minus d over 2 times m minus 1, whatever. F, okay, some constant depending on f. Okay, so you see, each of these coefficients, each of the coefficients of the linearity now depends on tau, and depending on the dimension and depending on m, they're going to have different behaviors. So what is it that we observe? So for example, in dimension d equal to 1, what happens here for the square? This is blowing up. So in particular, this suggests that the nonlinearity and already the quadratic term is going to be the dominant term of all, because this is the term that explodes the worst. And so this is the equation is said to be relevant, or in the language of regularity structure, it's subcritical, even though, I mean, this is misleading because regularity structure would be sending tau to 0, not to infinity. Anyway, okay, so the nonlinearity should be relevant, and the most relevant term should be the quadratic. What happens in d greater or equal to 3? Well, in d greater or equal to 3, all of these coefficients are going to 0. So formally, we expect that the nonlinearity, no matter what you do, is irrelevant. So, okay, and this is the so-called supercritical dimension. And what happens in d equal to 2? Well, in d equal to 2, again, here we still have terms which are vanishing. But the first term is scale invariant. So again, the only one which is sort of order 1 is the quadratic. And the equation is said to be marginal. And this is the critical dimension. And this is precisely the dimension at which we will focus on. Let me also add, I mean, clearly, if I look in dimension 1, and imagine for a second that I'm looking at a function f whose second derivative is 0. What this heuristic would say that, okay, I need to look at the next relevant term. So, but now, in dimension 1, the next relevant term would become the cube. And so this is sort of again, the equation would be critical. And if instead I look at higher order term, well, they're all going to have somehow a vanishing constant multiplying whatever nonlinear term you have. So some of the picture is a bit richer than just, you know, this splitting in the dimension. It might depend on certain features of your function f. Okay, but now there is a big problem with what I've just said, and the big problem is that none of this makes sense. So, and the reason why it makes no sense is because the noise is too rough. As I said, it's a space-time Gaussian white noise. It has infinite variance at every point, so there is no way. Okay, but at the same time, the universal fluctuations. So somehow what we want to describe are the universal fluctuations of the Burgers equation. It's not that the equation itself is any special. So what's special, what's important is that the large-scale behavior of the equation should be shared by all the systems which enter the same universality class. Okay? Okay, good. But so if this is the philosophy I need to go for, at this point what I can do is, well, I simply regularize my equation. I obtain an object which is well-defined and it's meaningful at the microscopic scale, and then I try to take the limit. And okay, and this is precisely what we'll do. And we'll do it in the following way. We take rho, which is a mollifier on Rd. Well, and by the way, the equation I'll focus on is dimension 2, but a lot of the things I'll say from here and up to a point is going to hold in any dimension. So I fix a smooth mollifier, and I look at the following equation. So now it is going to be at scale 1. And let me add an f. So I keep the dependence on f. And then I want also to make a choice. So my vector w, I'm going to choose it to be precisely the direction E1, like here. It doesn't matter because both the noise and the Laplacian are rotational invariant, and I can always, you know, apply a rotation to the coordinates and, you know, fix that value. Okay. So now I look at D1, and then I do a double mollification, and then I mollify f at eta 1 plus. And here, I'm going to have the noise mollified at scale 1. Okay? So now, I'm mollifying the noise. So now, this is a regular field. It's continuous in space. And I'm also doubly regularizing the equation. Okay, and I want to keep the dependence on f. Yes?
Why would you want to mollify f as well? It was already kind of smooth function.
Very good question. And indeed, the reason is that there is one property that I want to keep from the microscopic system. So the microscopic system has product Bernoulli as an invariant measure. This equation, if I mollify also only the noise, has no invariant measure. If I mollify nothing and I look at the equation bluntly, then one can sort of guess that white noise should be invariant. I want to keep this property, so to keep it, I do this. You know, yes, it's not I mean, why not? as long as I see the essential feature, I want to start from something on which I have some control. But if I could remove it, I would do it. Yes. Okay.
It's equivalent to the if you put spectral cutoff.
So meaning if I do a cutoff in Fourier? Yes, well, almost. So, okay, I'm taking rho compactly supported and smooth. Exactly. So I would need a smooth cutoff. Yes. So yeah, this is somewhat. It's convenient because it like allows us to do a couple of things, but it's not crucial. We could. Okay, no, we couldn't do hard cutoff for generic f and in infinite volume. I mean, somehow, if you want to make sure that the equation is, I mean, can be evaluated at points, which is going to be important in something I'll say, then it's better to work with a smooth cutoff. So that, like, actually, you know, if I look at eta 1 tx, this is, you know, a well-defined random variable. Okay. Okay, and so indeed, thanks to this choice, eta can be evaluated at points. Very good, and one can prove under quite general assumptions on f. We don't require, I mean, we require it to be smooth, but it can grow essentially arbitrarily fast at infinity, not faster than a Gaussian. That's all, than an inverse, like an exponential square, so of x squared. Okay, I don't know, if you have a function which is worse than that, and you really obtain it as the hydrodynamic limit, then we can discuss on how to improve this result. But somehow, like the assumption on the growth is good, at least in my view. Okay, the smoothness of f is not great, so one would like to have the result even without imposing f smooth. But anyway, so what we can prove is that indeed, so eta is well defined. It is well defined for all globally. And indeed, because of the growth assumption on f, so which are very mild, the result is non-trivial. But okay, so it's globally well defined, and it's Markov. And maybe indeed, so the point which is crucial for us is that it has an invariant measure which is explicit. An invariant measure is, okay, so I'm writing it very little, but it's mu convolved with rho, and rho is the same modifier, and mu is a spatial white noise. And these are several advantages. But okay, somehow we are starting, it's a smooth white noise, it's a Gaussian process with a decent covariance function, okay? Very good. So now we have a microscopic model which is well defined, and we want to study we would like to address the questions that I mentioned. So we want to know the non-linearity is relevant, we want to know the scaling exponents and the large scale behavior. To address at least the first two of these questions, a convenient observable is the so-called diffusion matrix. Now, this is a matrix which depends on time and is defined as follows. X. I mean, it's not a crazy object, okay? So what we're doing is simply, I want to look at the 2-point correlation function of my Markov process, starting from my invariant initial condition, and I want to see how this 2-point correlation spreads in space as a function of time. I mean, if you think of this simply as a Gaussian density, what I'm looking at is simply the covariance matrix of my Gaussian. This is what it represents. And indeed, this is precisely the case if you take the capital F to be equal to 0. So what you can show is that if f is equal to 0, then this d of t is nothing but the identity. Okay? And this is convenient. It's a convenient observe. Yeah?
That would be the position of the second class part, right?
it would be, exactly. So in the case of ASEP, this object would really be, I mean, you can prove that these correlations are positive. And so this is indeed the position of the second-class particle. It gives you the transition probabilities of the second-class particle. In the continuum, it's not true anymore because we don't know how to prove, and it might not even be true that this is positive. So we can't find, and it's a bit of a pity. We were trying to look, but somehow the fact that we're taking sort of this non-local approximation of the non-linearity doesn't help. Yes. Right. And so why is it also convenient observable? Well, because if I want to set apart the linear behavior and the nonlinear behavior, well, I need to analyze this matrix. If I prove that this matrix for t going to infinity has constant entries, so they are order 1, well, then I have something which, you know, it's somewhat diffusive, or at least it should behave as the linear system. If there are entries which grow, we're in a super diffusive regime, so at least we know that it's different from the linear dynamics. If it goes to 0, the same. So if one is super diffusive, the other is subdiffusive. But this matrix is interesting also for another reason, meaning, so if you are able to describe, like to obtain the asymptotics of this matrix, then you know precisely what are the scaling exponents. Okay? So somehow it's an interesting object. And we didn't invent it. It was present in for microscopic systems for a very long time. Okay, good. So now we have a microscopic system which is well defined, and we have an observable thanks to which we can check some of the properties, or we can try to address some of the questions we're interested in. So before moving on and tell you what we did, let me go over what's known already, and I'll try to be relatively brief. So let me take, okay, so we want to answer essentially 4 questions. So let me look at first d equal to 1, local solution theory. So what do I mean by this? I mean, okay, so you see here, I performed a modification. Is it possible to avoid it? And let me say, here I want to look at first my f of eta is simply equal to lambda eta squared, so in the quadratic case, okay? Now in this specific case, I can simply take rho in dimension 1 to be the delta function. This is the result of, well, I'm not going to write them all. There is a long list, Martin Hairer, Gubinelli-Perkowski, Milton and Patricia, and Perkowski and Gubinelli, and so on and so on. So there is indeed a well-defined solution theory, so which means that I can start without taking any modification. That equation is well-defined, yes, by understanding the product correctly. Good. So then diffusivity matrix. Well, is it diffusive? Is it super diffusive? Well, this was conjectured already in the paper by Van Beer and Kutner and Spohn, and it was recently proved. So what's been shown is that d of t behaves as t to the 1/3. So which means that not only it is super diffusive, but it's super diffusive at a polynomial scale. And this is a result which was first obtained by Balázs, Palestrante, and Quastel in 2011, and more recently by Dallap, Gu, and Komorowski, using completely different techniques, both of which very interesting. So it's indeed super diffusive, and this is what leads to the scaling exponents, which is famous 1, 2, 3 scaling of the KPZ. So now, what about the scaling limit? That's exactly the KPZ equation, exactly.
Not S, just.
No, it's exactly the KPZ equation, but then, yes, it's exactly the KPZ. Yeah, right, this is something I haven't mentioned, that's true. So indeed, in one dimension, this is nothing but the derivative of a KPZ equation. But let me stress, the connection is lost the moment we go to dimension 2 and higher. Yeah, that's it, yes. So what is the scaling limit? The scaling limit is the so-called KPZ fixed point. Again, so, and this is a genuinely non-linear fixed point. So somehow, in the right scaling, sort of the linear part of the equation, at least formally vanish, So okay, it's been described by Remenick, Quastel, and Matetsky. The object and then the scaling limit of the equation was also shown. What about, okay, so what about generic f? So what happens for generic f? Okay, and now I'll cheat a bit. So in dimension 1, there are many results, but all of these results somehow work under the assumption that I take my coupling constant to be 1 over square root of tau. So I'm in the so-called weak coupling regime. Somehow I'm looking at small scales, but they can show that indeed sort of the physicists were almost right, in the sense that it's true that the quadratic term is the dominant term, is the term that is the most important. Okay, it's not proven in the KPZ scaling, it's proven in a slightly different scaling, but somehow this is what the result suggests. Now, what about dimension 3 and higher? Well, dimension 3 and higher, there is no solution theory, and solution theory is not even expected. We are in the supercritical dimension. The equation is way too bad to make sense with rho equal to delta 0. Okay. What is dt? Well, dt, this is constant at large scales. I mean, writing it like this, but let me write it this. So somehow we know that at large scales, the process is diffusive. This was shown for the SPDE by myself, Fabio Toninelli, and Massimiliano Gubinelli, and the quadratic non-linearity. But like for ASEP, there are many results by Claudio, Stefano, Lavara, Daniel. There is a long literature.
So what's the diagonal, the matrix D?
Yes. It is diagonal because I'm choosing this W to be the first coordinate. So if I had an arbitrary W, then no, it wouldn't be diagonal. Yeah, I mean, it would be diagonal in the direction W. I'm already sort of orthogonalizing it. Yes. Okay, and what is the scaling limit? It's Gaussian. It's Gaussian, so indeed the physicists were somewhat right. So the sort of like, at least for the quadratic nonlinearity, the nonlinearity is irrelevant. But you know, it's wrong to say this because it's not true that this is vanishing. So this is not going to 0. This is somehow this object is going to does contribute to the limit because this D is not the identity. And okay, generic F, question mark. What about D equal to 2? So we are at the critical dimension. This is precisely the dimension at which all the various local well-posedness theory break down. And okay, what about the diffusivity? Well, for the diffusivity, again, so there is the conjecture by Van Beijren, Kutner, and Spohn back in '86. And let me say that they also predicted this T to the 1/3 the year before the KPZ paper, just to say. And so what is it that they conjecture? Well, they conjecture that, well, still, the behavior of it at large scales is super diffusive, and it's super diffusive in a very precise way. So they conjecture, so this is the conjecture, that the first entry, so which is indeed the direction of the W, should grow as log t up to a specific power 2/3. And this conjecture was partially proved. It was like there is a result by De Gasperi and Hauenschmidt, in which somehow what they showed is almost this, so that if I do the 2/3, this is essentially the right order up to log t to the 3 plus delta and log t to the -3 minus that, something like this. So essentially what they're saying is that up to lower order correction, and you can add another few logs maybe, the conjecture indeed is true. It holds. And this is a result both by De Gasperi and Hauenschmidt for the Burgers equation, and by Yao. It's a remarkable work of Yao in early 2000 in which essentially he obtained the same result. Okay, what about the scaling limit? Open. And what about generic F? Open. And this is precisely where we come in. So this is sort of the things we want to try to address are precisely these 2 points at the critical dimension. And I want to mention something about what happens in dimension 3 and higher, or in dimension 1, we'll see. Okay. So the first, our result is the following. What we prove is that for the stochastic Burgers equation with quadratic non-linearity, and this is myself, Moulard, and Toninelli, 25. Then what we prove is that dt is asymptotically equal as t goes to infinity. This indeed, there exists a not there exists a constant. We have a constant, C effective, lambda to the 4/3 log t to the 2/3, and then 1 plus little of 1, 0, 0, 1. So somehow what we obtained is the asymptotic expansion of the diffusivity matrix. Not only we obtained the correct order, but also the prefactor. This lambda to the 4/3 is interesting because we think it's more universal than just dimension 2. Somehow the same thing you see in dimension, so the same value of lambda of the coupling constant you see in dimension 1, precisely the same. And it should be an effect of the fact that for both our equation and in dimension 1, the microscopic diffusivity is vanishing. So the microscopic, the original Laplacian and the original noise are simply going to 0. And this little o1 is quantitative. So, well, I'm not claiming any optimality, but we can prove we have a precise rate at which it's going to 0. It's 1 over log t to the 1/6. Might be better than that. But OK, we have a quantitative result. OK, and now, good. So, but the importance or the interest in this is, OK, apart from somehow addressing this conjecture, is that we know precisely how we need to scale our process in order to see the limit. And pay attention. So we know that in one direction, the system is diffusive, while in the other direction is superdiffusive. So if we did simply a superdiffusive scaling, so we don't want to kill the diffusive part. So what I mean by this is that, so how should I rescale my eta at tx? Well, on the one hand, we clearly want to look at large time. So we take tau t. At the same time, somehow, we want to simply slightly modify the diffusive scaling. So I'm going to have a tau to the 1/2 x. And let me put here another tau to the 1/2. But now I need to modify the scale so that I can sort of tame the superdiffusivity in the first direction, but somehow scale it diffusively in the other. So here I put a matrix, r tau to the minus 1/2. This depends on tau. And what is this? Well, this is essentially like the inverse of the d. So somehow I take my r tau as 1 over log tau to the 2/3, 0, 0, 1. So in the second direction, I scale it diffusively so that I don't kill the part of the dynamics which is diffusive in nature. And in the first direction, instead, I want to tame the growth coming from the superdiffusivity. And OK, but now now I need to adjust the size of the fluctuations, and I need to adjust the size of the fluctuations in such a way that the spatial white noise converges to an actual white noise, which means here I need to take log tau to the 1/6. OK? So this is the scaling.
So you're working with modified equations?
Yes, I'm working with the modified equations. And this is really, I'm taking so this is sort of my eta 1. And what I'm doing simply, so I was at scale 1, and now I'm going to large scales. And what's interesting, and now I'm going to large scales. So I'm really, so this is just by scaling. I'm not touching the equation in any way, but just by scaling, I'm doing this. And let me say that, but upon doing this, all the modifiers are formally going to 0. So to the delta function. OK. And so then what is it that we prove for the OK, so what is it that we can show? Well, we can show that indeed if OK, so the second theorem, and this is still, it's in 2 parts. Cannizzaro, Moulard, Toninelli, 25. And so in the first part, what we show is that under that scaling, so if p tau is the semigroup of eta tau, then what we show is that the supremum over T, okay, P tau F minus T effective TF is converging to 0 as T goes to infinity, as tau goes to infinity. And what is P effective? Is the semigroup of the following equation. What is this? The effective is equal to simply C effective lambda to the 4/3 0, 0, 1. So this is already present in the paper, and what is this saying? This is saying that like the semigroup of my rescaled stochastic Burgers equation converges to the semigroup of an effective equation, which is Gaussian, but in which whose coefficients have been modified. So they are somewhat renormalized, and okay, and it's no surprise that the sort of the renormalization or the effective diffusivity I see in the limit is still 1 in the second coordinate because it's the original one which has been untouched, and it contains this factor in the first coordinate. One thing which is not in the paper yet, and we'll add it soon, 26 plus, hopefully, yes, early 26, is the following. So what we can also show is that we have this type of convergence. Of f of eta tau minus f eta effective. Sorry. You know, and this converges to 0. I mean, this second part is so the convergence of the semigroup implies essentially the convergence of the finite dimensional distributions. Okay, what we can prove is now we can upgrade it to a convergence of the law of the entire process. And this type of convergence is sort of what's, I mean, it's semi-quenched. So it's in probability with respect to the invariant, or in L1 with respect to the invariant measure. Okay. It's not quenched, it's not annealed, but it's better than annealed. Okay, so this is sort of so somehow what was missing, and it's not in the paper, is tightness, which now we have a way to prove. Okay, so this is somewhat the picture. So we have characterized and identified the large-scale behavior of our system. Now, what about the question we started with? So, you know, this is in the case in which we have the quadratic nonlinearity. What happens if I replace this quadratic nonlinearity with something else? Well, what we can prove is the following. So I'm essentially trying to address this question here. Is the following. So this is a joint work with Tom Close and Cantat-Moulard. We have the following theorem. And this is early 26. So if I consider the equation that I erased, so we have dt eta 1 f equal to Laplacian plus d1 f eta 1. Now, and if I scale it super diffusively, so the same scaling as here, okay? Then, okay, I'll write it in a rather, slightly weird way, the result, but I want to explain why. So again, maybe here there is an expectation. So what we show is that the semigroup P tau converges to 0. What am I trying to say with this? What is this? So this is the same as this. So in a sense, if I take a generic nonlinearity, so this is asymptotically behaves the same as the one with a quadratic nonlinearity, but in which the lambda needs to be chosen not as the second order in the Taylor expansion, as sort of the heuristics was suggesting, but as the second coefficient of the Hermite polynomial, or like of the expansion of f in Hermite polynomials. So, well, this is nothing but x squared f of x dx. So, in other words, so the physicist's conjecture is partially correct, or the derivation is partially correct in the sense it's true that the quadratic term is the leading term, but it's not true that the expansion I need to look at is the expansion in Taylor. It's the Taylor expansion. I need to expand with respect to the measure, which is somewhat more natural for the equation, which is the measure given to you by the invariant measure. We know that the invariant measure is Gaussian. So that's the reason why we see Hermite polynomials popping up. So this is the partially correct. And okay. And the reason why I wanted to state it this way is because really, so what it is the approach of our proof. So we compare the generic, the equation with a generic nonlinearity with the one in which the nonlinearity is simply quadratic, but taken in the right expansion. Okay? And the rest can be shown, it's really relevant. So somehow the conjecture of the derivation is not fully wrong. Okay?
So is it square, not x squared minus 1 there?
Yeah, it's yes.
The argument was based on scaling, so what was it breaking?
No, I mean, the scaling doesn't break at all, but the scaling was wrong in the sense that, like, no. So, okay, the scaling was wrong for this equation because now you need to adjust the scaling logarithmically. And anyway, what happens is not that sort of, the fact that these scaling terms are going to 0 is only formal. What actually they produce, so that we had factors of the form tau to the 1 minus d over 2 m minus 1 times, I don't know, my nonlinearity, which is W scalar gradient eta to the m. What happens is not that this is going to 0. What happens is that, this is my next result, but this is order 1. In this specific scaling, since it's superdiffusive, this is really going to 0. But this is an effect of the superdiffusivity. And the same should happen in dimension 1. That's the reason why in dimension 1 they proved a similar result. Do I still have 2 minutes? 3 minutes?
Yeah.
Yeah? Okay, so right, so this is sort of this somewhat complete the picture in dimension 3, or at least it completes the picture as long as clearly this needs to be different from 0. So what happens instead if this is equal to 0 and the next is non-zero? We don't really know. But what I want to state is indeed a result that somewhat captures this last effect. It's not a deep result of any form. It's just to show that there is a bit more to be found. And let me write it here. So in this equation, let me write this term as nf1 of eta. And we have the following, proposition. It's myself and Tom Closer. And I'm not sure if he's, yeah, okay, nothing. So 26 plus plus. And what is it that we show? Well, okay, so let's assume that we are in one of the following situations. Either we are in dimension 1 and the second and the third Hermite coefficient are equal to 0, or we are in dimension 2 and then the second is equal to 0, or we are in dimension greater or equal to 3, and here whatever. And let me assume for convenience that actually f is a Hermite polynomial. Of order m for m in this range. So somehow, in this case, m is different from 2 and 3. This is m is different from 2, and m is whatever. Then what we can prove is that if you take now the solution to this equation, now we are in any of these dimensions, and we scale it diffusively, then what we have is that this eta tau is tight. Okay, so somehow we know that there exists at least, it's compact, we have scaling limits. We can't describe what the scaling limit is unless only in dimension d equal to 2, and for these d equal to 3 and higher, but m is equal to 2. Otherwise, we don't know. But we have a second property, which is the following. If I look at the expectation, or the second moment, of my non-linearity tested again in test function squared, we have upper and lower bounds, which are c t phi squared, and this is different constant phi squared. What is it that I'm trying to say? I'm simply trying to say what I said like 1 second ago. So in any dimension, or like with these specific choices of your function f, not specific, but at least satisfying these conditions, then we have tightness, good. And we also know what this says is that somehow the system is diffusive, in a sense that from this it's possible to deduce a bound on the diffusivity matrix that we saw before. And thus we strongly believe, or I strongly believe, that it's going to be Gaussian, but I don't know how to prove it. So, or better, I know how to prove it if you take m is equal to 3 in dimension 3, which is really unsatisfactory. Okay, but somehow, right, so with this I think I'll stop. Thank you very much.
Okay, so any questions?
In 1D, if you have two coefficients 0, you are losing.
Yes, I mean, even if you have one coefficient, if C, okay, I didn't say, but like if C3 f is different from 0 and C2 f is equal to 0, then we can prove a similar, so we can prove logarithmic superdiffusivity, and we expect again Gaussian behavior. So, but if the quadratic term is 0, somehow you lose KPZ. This is for sure. Yes. Yes.
You said, okay, the first term is 0, but it's strictly. Then the second, you said, okay, it's not 0, but you can think of a frame, frame, so you can forget about it. You moved on, but that was the most relevant term.
Potentially.
And I wanted to ask if the fact that the coefficient is not the Taylor, but the Hermite, is related to the fact that you got the first term.
No. I mean, what you need to do, but it's true that in principle, indeed, if you do the expansion in Hermite this time, you want to sort of compensate every term. So it's not true that the thing you need to compensate, so that the linear term is just, you know, the first term of the Hermite of the Taylor expansion. Again, you would need to do the Hermite expansion and then go into a moving frame with respect to that velocity field. So I don't know if it's clear. I mean, it's connected, but somehow the fact that you're looking at Hermite polynomials I mean, it's not related to the, I mean, it's related to the way in which you choose the velocity, and so in which you choose the moving frame, but it's not related to the fact that you see Hermite polynomials. Somehow the Hermite polynomials are somewhat built in. It's a microscopic sort of, yeah, no, that's it. So it's a somewhat built-in, yes.
Any other question?
What's the idea of the proof? Like,
Yeah, it's true. It's something, yes, it's a good, very good point. I mean, okay, do we have another hour or so? No, okay, very briefly. So, okay, so the idea of the proof can be boiled down to that. So what we do, our analysis is at the level of the generator of the equation. So we have a Markov process, we have a well-defined generator. Now, there is the big difficulty is that this generator is horrible. And what you want to prove is that somehow you can approximate this generator so that, and at the end of the day, what you want to see is a very simple generator, which is the generator of the linear equation. What we prove, and I mean, this is not the main point, but it's sort of the highlight, is that if I look at the nonlinear dynamics, what we show is that this is approximated by sort of like an effective equation, an effective generator, but this depends on tau, and it's linear, but with tau-dependent coefficients. So this is the generator of an equation, essentially as the one I wrote before. This is going to be now it effective plus the noise. And this object is non-homogeneous, and it somehow contains 2 bits. So this D is going to be equal to, well, you have plus a certain G of tau. And this is going to depend on your mode. So this is the microscopic diffusivity, the one that is really going to 0. And this term is a term that, like, if you simply pass tau to infinity, it's going to give you the limiting diffusivity, but it's telling you how scale by scale sort of this generator is affected. So really, once you have this, you're done. But like proving this, some of this is based on a recursive structure that the generator has. And since it's based on generator, somehow the approach works also for other systems, which I haven't mentioned, but okay, a bunch of them, finite.
Okay, any other question? Well, if not, let's thank Guiseppe again.
Thank you.